So in the yesterday server, okay. So in the yesterday server, we have discussed about see, we have discussed about the common base configuration, right? So in the yesterday server, if you see, just I will try to conclude this one. Okay. So we have discussed about the common base configuration. Okay, we are making the base as a common between the input and output. Therefore, we are going to call it as common base configuration. Okay, so for this common base configuration, we need to run the emitter base junction as a forward bias, collector base junction as a reverse bias condition. Okay. So for that reason, we have given the emitter voltage. We made this emitter voltage and collector voltage. This emitter base junction as a forward bias and collector base junction as a reverse bias. So whatever our aim or our object is, we need to draw the input and output characteristics for every configuration. That is for a common base, common emitter and common collector configuration. To draw the input and output characteristics, for the input characteristics, the input voltage is VBE, that is the base to emitter voltage, and the input current is IE, that is the emitter current. Similarly, output voltage is VCB and output current is IC for output characteristics. So we have drawn the input characteristics. These are actually the input characteristics, considering the x-axis as VBE and y-axis as IE. So this current is in terms of milliamperes, right? Only the base current will be in terms of microamperes, emitter current as well as the collector current will be always in terms of milliamperes, because base current will be very, very less because it have a very narrow width. For that reason, you will get very less amount of current. But emitter current and the collector current will be always in terms of milliamperes. So if you observe clearly, whenever you are changing this VCB is the voltage between the collector to base. Okay. VCB is the voltage between the collector to base, collector terminal to base terminal. So when you're changing this, if you want to change this collector to base voltage, means you need to change this VCC. Okay. Whenever you are changing or you are increasing this VCC voltage, what happens? The reverse bias voltage, that is, you are increasing the reverse voltage. So whenever you are increasing the reverse voltage, the depletion layer will increase, which makes the width this one as an arrow. Therefore, you can see the emitter current is started increasing. So whenever your VCB is increasing, the emitter current is increasing. So this is from the input characteristics. So if you make it as a slope, and if you're trying to find out the input resistance, that input resistance is change in the VBE, that is delta VBE divided by delta IE, will give you the input resistance, right? Which is a very low resistance. Now coming to output characteristics. So we already know output characteristics is drawn between the output voltage and output current. Output voltage is VCB, output current is IC. So VCB will be in terms of volts, ICB is in terms of milliamperes. So we have three regions which it is going to cover: active region, saturation region, and the cutoff region. So in the active region, whenever you are changing this VCB voltage, the collector current is exactly the horizontal curve, which it is exactly parallel to this x-axis, right? Which it is exactly parallel to this x-axis, and it is constant. Okay, but whenever you are increasing the emitter current, the collector current is also going to get increased, because we already know that collector current is equal to alpha times of emitter current. So when the emitter current is increasing, collector current will also increase. If you are considering the alpha factor as 1, obviously the alpha factor will be very, very less value. It will be always equal to 1 or less than 1. So we have discussed also the saturation and the cutoff characteristics. Now coming to voltage amplification. Voltage amplification, just I took one example. That is how we can able to amplify the voltage, how we can able to increase the voltage from input side to output side. So we took one voltage as a 5 millivolts as an AC signal. We have not connected any BEE or VCC. Just we have removed those DC voltages and have connected one AC voltage and have connected my load here across the NPN transistor. So whenever I am applying the 5 millivolts, considering the input resistance as a very less value, I will get the input current as 0.5 milliamperes. So we already know that output resistance is very high. Therefore, you considering this alpha factor, that is the gain factor, is equal to 1, you're going to get output current is also equal to 0.5 milliamperes, right? Therefore, output voltage will be approximately, you're going to get 50 volts. This indicates that you are increasing the amplitude of the voltage from 5 millivolts to 50 volts by using this NPN transistor. Okay, this is the use of a voltage amplification. So this is nothing but a concept of common base configuration. Okay. Now let us try to discuss also another important factor about the common base configuration, that is called as an early effect, right? Or we are also going to call it as a punch through effect. We're also going to call it as a punch through effect. So what is this early effect? So this early effect is not, it is not going to come under the common emitter configuration. This is actually come under the common base configuration only. Okay. This is actually the common base configuration effect itself. So this will come under the common base configuration. Just I took the same concept what we have done here. See here we have a emitter voltage which we made emitter base junction as a forward bias. Similarly, collector base junction as a reverse bias, and this is a VCC. So we also have emitter current, base current, and also the collector current. Base emitter voltage, nothing but an input voltage, because the current is from base to emitter. For that reason, we have indicated here as a positive and negative. Okay, this is plus to minus because current is moving from like this, so positive minus, so VCB is the voltage. Now what happens, what is this actually effect? So this effect will be always when you are increasing the voltage. For example, have increased this VCC, or nothing but you are increasing this VCC means nothing but you are increasing this VCB voltage. Okay, so when you are increasing this voltage, whenever you are increasing this voltage, what happens, this, there is a depletion layer for this junction. Okay, we are going to call it as a collector base junction. There is a depletion layer. So whenever you are increasing this voltage, gradually this depletion layer is increasing. Whenever this depletion layer is increasing, what happens, this base junction width is getting so much narrow. You can observe that important point, base junction width is decreasing when you are increasing the reverse voltage. So still I have increased, so still I am increasing means it is also getting increased. So whenever this depletion layer is increasing, this base width, you are also going to call it as a base width modulation and also called as early effect. So this is getting less width, narrow width. Therefore, what happens, we are going to call this condition as early effect and also called as a base width modulation. If you see the lecture notes, see here early effect or base width modulation. So whenever you're increasing the VCC, what the space charge width between the collector and base, that is between the collector and base, is this one, collector and base. So between the collector and base tends to increase, that is width is increasing, that indicates the depletion layer is increasing, with the result that effective base width decreases, with the result that this base width will be get decreases. We are going to call it as a base width. So this effect is called as early effect. We are going to call this effect as early effect. Okay. So these are the conditions. If you see the decreasing, what happens, what is uh, the factors affecting when the base width is decreasing, what happens, the recombination will be get decreases. Why? Because we now whatever the electrons we have, it should need to recombine with the holes, because the majority carriers of the n type is going to recombine with the holes, but recombination will be very less because the width in the previous case compared to the previous case it reduced. So whenever it reduced, what happens, automatically the base current will also reduce. Okay. So that indicates recombination will get reduced, and therefore alpha factor, less chance of recombination is going to take place. Therefore alpha increases. Why alpha increases? Because base current is decreasing. So when the base current is, oh sorry, I have written is increasing. No, the base current will decrease. This base current, so this is actually a direction, please don't get confused. This base current magnitude will decrease. So whenever this base current magnitude is decreasing, the collector current will increase. That indicates the width is very less. Therefore, not just the 95%, 98% of the electrons will move from emitter to collector, having a very less width of base. Okay, so therefore this increases. Therefore, there will be increase in VCB voltage. Okay. So gradient increases in base and current of minority carriers injected from the emitter junction increases. So extreme low voltages. See what now we are going to call it as a punch through effect. Why we are going to call it as a punch through effect means, so now we have increasing. So still I am increasing. If you are increasing still and still, therefore the base width is going to decrease, and at one point At one value of voltage, what happens? Base width will get vanished. Depletion layer of the collector base junction will be so much high, and we are going to call that as a breakdown is going to take place. That breakdown we are going to name it as a punch through effect. So whenever this collector voltage is increased beyond the range, then the base junction will get vanished at one value of voltage, and it is going to the transistor will face the breakdown, and their breakdown is going to call it as a punch through effect. Okay, this is just like a punch, pin punch. We are going to call it as a punch through effect, right? So this is actually the one important. He's going to ask for early effect or base width modulation or punch through effect for 5 marks or 2 marks question. Okay, you need to write this theory. Okay. So this is about the early effect or a base width modulation, which it relates to the common base configuration. Now let us try to understand. Now let us try to understand about common emitter configuration. Now let us try to move to the common emitter configuration. Okay, so whatever here, just we are rotating this one. What we have NPN transistor base, you have at the P you have a base, at N you have emitter, at 2 you have N. Okay, okay, just we are rotating this one. When you are rotating, you need to make this point as now emitter. If you want to make this point as emitter, means because it is a common emitter. Common emitter means emitter should be a common with respect to input and output. That means just you are rotating that one. If you see here, see, this is a common emitter. You made this as a common for input as well as output. Okay, this is a base, this is a collector, and this is emitter. Right. So for this one, you need to find out, you need to draw the input characteristics as well as output characteristics for this common emitter configuration. See, very important topics. It is easy as well as you can draw the characteristics as well as you can write down the points very easily. Okay, just you need to understand the concept, and please don't neglect these topics. So just this is an NPN transistor. You can see this is NPN. Just have drawn this like this diagram. You can see. So we have an NPN transistor. Okay, for this NPN transistor, we have a collector voltage. We also have base voltage. Now, if you see here, now the emitter is acting as a common. So this side it is input, and this side it is output. Okay, this is input side, and this is output side. This time, this is that is input side, and this is output side, right? So if you want to draw the characteristics, what you need to indicate? You need to indicate the voltage as well as the current. So if you want to draw the characteristics, you need to indicate the input voltage and input current at the input side. Output voltage and output current at the output side will give you output characteristics. So if you see clearly, the base is just we have assumed one resistance as RP, and we have also assumed one resistance as RC, and this is the base voltage. This is VBB is the base voltage, and VCC is the collector voltage, and the voltage drop between the base and emitter is called as the VBE. If you see here, plus and minus. Similarly, the drop between the collector and emitter is going to call it as a VC. We also have one voltage. We are going to call that voltage as plus minus VCB. Okay, this is also one voltage called as a collector to base voltage. This collector to base voltage and collector to base voltage and base to emitter voltage. This summation will give you the VC. Okay, please don't get confused. If you want to know VCE, just I write here VCE. So VCE is equal to, what is VCE? VCE is equal to VCB plus VB. VCB, that is voltage, will give you VC, collector emitter voltage, right? Okay, so now we need to draw the characteristics. What is input voltage here? Input voltage is VBE, and what is the input current is IB. If you see the current direction, this is actually NPN transistor. If you see the current direction, if you draw this as a schematic diagram, the same diagram I have drawn here. VBE is the base to emitter voltage, VC is the collector to emitter voltage, and here we have another voltage called as VCB. I have already told we have this voltage, collector to base voltage, that is VCB, and this is the base voltage, this is the collector voltage, base resistance and the collector resistance. This is the base current. If you see, this is the base current. The formula is not going to change for any configuration. If you see, the summation of the collector current and the base current will give you emitter current only. But in this case, see, in the common base, what is the input? In the common base, if you see here, the common base config, this is actually for common base. In the common base, what is input? Input is the emitter current. Okay. In the common base, if you see here, the input is the emitter current and output is the collector current. But whereas in the common emitter, base current is the input current. Please don't get confused. Base current is the input current and output current is the collector current. Now we are not going to discuss that much about the emitter current because now this is a common. Okay, so whatever the voltage to which junction you are applying the voltage, that current is the input current. To which junction you are applying the collector voltage, that current is nothing but an output current. Okay, so this is the base current and this is the collector current. So base current is going to act as an input and collector current is going to act as output. Base voltage VB is going to act as an input voltage, collector voltage is going to act as output voltage. Now we will try to draw the characteristics. See, I have already told this is the same combination. How we are done, we made emitter base junction as a forward bias. Here also we made emitter base junction as a forward bias and collector base junction as a reverse bias. Okay, same thing we have done, that is emitter base junction as a forward bias. Emitter base junction the forward bias and okay, and collector base junction as reverse bias. See, we have done the same thing here. Okay, all the configurations we are going to make the emitter base junction as a forward bias, collector base junction as a reverse bias, because we would like to operate or make the transistor to be operate as act as an amplifier only, you know. Now coming to input characteristics. So okay, if we discuss about the input characteristics, I have already told input characteristics is between the input voltage and the input current. What is input current in this common emitter configuration? Hassan, please take down the roll numbers who are present and who have not joined to the audio. If not, you can take a screenshots. Who have not joined to the audio, please don't consider those roll numbers as a presentees. I can see here, I think you can also visible here. Who have not connected to audio means you could not able to see in the right hand side as a mute symbol. Mute or unmute symbol, it is not going to visible. That indicates they are not listening the class. Okay, rule number 121, rule number 190, rule number 199 and A7. These are the 4 numbers who are not listening to the class. Okay, they have not connected to audio. Okay, they have joined but they have not connected to audio. Please don't consider these rule numbers as a present. Okay, I'm making it as a screenshot and you can also send me the screenshots. Clear? So now coming to the input characteristics. Okay. Now Hassan. Now coming to the input characteristics. In the input characteristics, we need to draw the characteristics between the base emitter voltage and the base current because it is the input voltage and this is the input current. So we already know input current is base current, which it will be always in terms of microamperes. Okay, because it is a very less amount of current. If you see, the current is very less here. So this amount of IB current is very less here. Okay, so for that reason we will always indicate IB in terms of microamperes. And if you observe clearly, we have a VC here. VC is the collected to emitter voltage. I have already told this is a collected to emitter voltage. Now in the previous case, that is whenever you have drawn for common base configuration, if you see here, for a common base, this is for a common base configuration. Okay, in a common base configuration, what happened under the common base configuration? In this case, the voltage is increasing. Whenever the VCB voltage is increasing, the axis or the characteristics are moving to the left hand side. Okay, here also When here the voltage is not increasing, here the voltage is decreasing from this point to this point and this point to this point. Okay, and these characteristics will also follow the forward bias characteristics of a PN junction diode. Okay, these characteristics will not change for an input because this will follow the same PN junction characteristics here. PN transistor. This is completely the forward bias, right? PN is a forward bias condition. Therefore, it will follow the forward bias characteristics of the PN junction diode itself. So for that reason, the characteristics are like this. But whenever the VC is varying, you see, when the VC is increasing, just you can assume that if we have this as a condition 1, at condition 1 we have this IB. So at this condition 2 and at a condition 3, when VC is increasing, what happens? This forward bias characteristics are moving to the right hand side. If you still increase, it will be like this. It will be like this. It will be like this. So whenever you're increasing this VC voltage, the axis, the characteristics are moving towards the x-axis. But in the previous case, when you're increasing the voltage, the axis are moving towards the y-axis in the common base configuration, right? But in this case, it is not going to happen. It is moving towards the x-axis. So why it is moving towards the x-axis? That indicates whenever it is moving, the base current is changing. You can observe this one. The base current is changing, right? That is, when you are increasing the voltage, the base current is getting dropped. The base current is decreasing. So why it is decreasing? We'll cross check what we are doing. You are increasing the VC. Okay, whenever you are increasing VC, the base current is dropping. Why it is dropping? We'll try to cross check here. We'll try to cross check here. So what I have written here, I have written when VCB is when VCB is increasing. So when this VCE is increasing, see, when VCE voltage is increasing from 1 to 10 volts or 10 to 20 volts. So when VCE is increasing, VB is remained as a constant, what happens? VCB will increase. If you consider this as a constant, if the VC is increasing, VCB will also increase. Okay, indicates this value is increasing, or nothing but this value is increasing. Okay, just I will take another color. This value is increasing, right? This value is increasing and this value is also increasing. So that means you are increasing this voltage. So whenever you are increasing the reverse voltage, what happens? This depletion layer, whatever you have drawn, this depletion layer will increase. So this depletion layer will increase and make this base junction as an arrow, which we have already discussed in earlier. Okay. Whenever you are increasing the VCE, the width of the collector base junction will increase. Therefore, which it makes the base width junction as a narrow, and whenever it is getting narrow, what happens to this base current? This base current will get decreases. You see here the base current IB. If you write here IB, this is the current IB, right? Okay. The base current now it will start decreasing. Here the same thing which we are seeing here, which you are watching here, the same thing. See here, whenever I'm increasing the VC voltage, the base current is dropping here, 0.1, 0.2, 0.3, 0.4, 0.5, right? So these are actually the input characteristics, okay, which we are going to draw in between input voltage VBA and input current IB, right? Now let us discuss about output characteristics. Now let us discuss about the output characteristics. So what actual output characteristics? Output characteristic is going to drawn between VCE and IC, because VC is the output voltage and IC is the output current. Okay. VC is the output voltage and IC is the output. You can see here VC is the output voltage and IC is the output current. If I increase, I think it is getting so much of zoom. Okay. So VC is the output voltage. It is so much of. Okay, VC is the output voltage and IC is the output current, right? So again, we have three regions here. I've already told you're going to have three regions. This is as active region. This is as active region. I'm going to write it as a capital A. And this is as saturation region, I'm going to write it as a capital S. Okay, and this part, the remaining part, is called as a cutoff region. I'm going to indicate with capital C. Okay, so these are again all the three regions which it will come under the output characteristics. So when it is operating under the active region, when it is operating under the saturation region, when it is operating under the cutoff region. So the only thing is, if you see, observe clearly, if you are comparing the characteristics with the common base, what actually the characteristics of the common base, just I'm opening that one, you see the output characteristics. See, in this output characteristics is exactly the constant which is exactly parallel to x-axis, but this is not happening in common emitter. You see, this is not happening in a common, this is not exactly the constant. Okay, this is not exactly parallel to x-axis, this is not constant. Okay, if you want, you can observe the difference. Okay, that means whenever you are increasing this VCE voltage, the collector current is also increasing. It is not remaining as a constant. Okay, when you are increasing this VCE voltage, the collector current is also increasing, which you can able to see in this characteristics like this. Okay, so why it is increasing? Whenever I'm increasing this one, what happening? I have already told, when we are increasing this VCC, the VCE will also increase. When the VC is increasing, collector current is increasing. Why the collector current increasing? Because the base width now became narrow. Now it became narrow. Therefore, not only the just 95%, the 98% of the electrons what are available in this P region will jump to the collector region, right? Because, only 10 minutes left, because the less recombination is taking place in the base width region, because you have the width is very narrow, therefore the recombination is very less. Therefore, most of the electrons are going to the collector region through the base, and therefore the collector current is increasing. Now this time the IC increases because of increase in the reverse bias voltage. Clear? So that is the thing what you are going to see here. That is the thing where the collector current is increasing, which is happening in the active region, right? And coming to saturation region, you already know when it is running, these two are running under the forward bias condition, automatically it will drop to 0. Okay, and in the cutoff region also, if you see in the saturation region, both are under the forward bias condition. So when both are under the forward bias condition, it will try to move, that is, it will try to increase with respect to the base current. If you see, at every point, the base current is changing. So with respect to the change in the base current, the value at the saturation, the collector current will come into that point. Okay, we are going to call this a saturation region. In the cutoff region, it is going to act, but it is exactly now, it is not increasing. You can see here, when the IB is exactly 0, the IE is also constant because there is no IB. If there is no IB, then IE is nothing but an is equal to IC, right? So this is nothing but an cutoff, active and saturation region in the output characteristics. And we also have what we can also write now. What we can write? So what is input current now? Input current is, output current is IC, which is equal to, so output current is IC, and input current is IP, and the current gain factor is beta. Okay, equal to beta into I. Beta is a current gain, where this beta, I can write it as beta is equal to IC divided collector current, that is output current, divided by base current. But whereas in the previously you have written alpha, how you have written alpha in case of common base configuration, you have written as output current divided by input current. Output current is IC, but input current is IE. Okay, not IB. Okay, so here this is in case of common base configuration. Okay, this is in case of common base. This is in case of common base configuration. Okay, this is in case of common emitter configuration. Anyway, the definition of any gain, current gain, is output current divided by input current. That's it. Okay, so but in the common base we are going to use alpha, In the common emitter, you're going to call it as a beta. In the common collector, you're going to call it as a gamma. Okay. Only the notations will change because to identify at which configuration the transistor is working. Okay. This is under the common emitter configuration, right? Okay. These are the input and output. See, the alpha value is a very less, that is which is approximately equal to 1 or less than 1. Okay, which is a less than 1. Beta value will be very high. Why the beta value is very high? It is a very high value. Okay, but it will be equal to 100 or 500 like this. Why? Because my alpha value is approximately equal to 1. Because I see what is collector current, which it will be in terms of milliamperes. If you see, the collector current is in terms of milliamperes, right? Emitter current also in terms of milliamperes, right? For that reason, milliamperes and milliamperes means you will get approximately the same value or less than or equal to 1. But coming to here, what is the collector? It will be in the range of milliamperes, but base current is not in the range of milliamperes, but it will be in the range of microamperes. Okay, and write that symbol here, which it is in the range of micro. Okay, you see the base current is in the range of microamperes. So milliamperes divided by microamperes means approximately you will get 1000 or 100 to 500. Okay, this gain will be like this. Okay, it may be 1000 also, like that. So this is actually the current gain in case of common emitter. So now just I will revise again. We have discussed about the Early effect and punch through effect regarding the common base configuration, and we have started about the we have discussed about the common emitter input and output characteristics. This is actually an NPN transistor, which the base emitter is again the forward bias, collector base junction is a reverse bias condition. This is BC is equal to the summation of VCB and VBA voltage. Okay, the base current, emitter current and the collector current. We are going to draw the characteristics for input and output. In this case, input current is the base current and input voltage is VBA voltage. And with respect to the increase in the VCE, there will be a drop in the base current, which we have already seen. Here also we have 3 regions. Output characteristic is drawn between VC and IC. Only 4 minutes left. And with respect to that one, we have there is an increase in the collector current, which we have already seen, just because of reduction on the base width narrow, which is a narrow base width. For that reason, the collector current is increasing. So we are going to write this. We are going to use this notation as a beta, where beta is the output current divided by input current, IC divided by IB, which it will be in the range of 100, 500, 1000 like that. And whereas we also have alpha, which we are going to use in a common base configuration. Because of having the same units, you are going to get approximately or less than equal to 1. Okay, so this is the thing what we have discussed. The same thing if you see here, common base plus alpha value, common base configuration. So don't get confused with this diagram. This is only the measurement of base to emitter voltage. This is the measurement of BC, collector to emitter voltage, to find out the base current and to find out the collector. Same thing we have discussed here. You can see here, which it is the largest current gain, because I have already told it will be around 1000 or 500. This is the beta, and the same points what we have discussed is there in this one. This is the relation between the beta and alpha. Okay. So we already know these characteristics. Both should be forward bias, both should be reverse bias, forward bias and reverse bias. So in the tomorrow's class, we'll try to discuss about the common collector configuration, right? Please all of you go through all the points, okay? And whatever you have doubts, you can ask me now. Please ask me doubts, okay? 99 is connected to audio now. If you are connecting, what you're going to listen 99? Huh? What are you doing up to now? Just you are joining, but you're not connected to audio. You're thinking that you will get attendance 99. I think, is she listening or not also? I don't know. See, 190 and 121. Yeah, and also 162 is also. So especially the 190. Okay. Hassan say that 190 rule number, because he told and he argued with me. by messaging that, sir, I have attended, I have attended, I have. See, not just inform him that not attending, not just joining the meeting. You should also join with the audio. What you're going to do if you join with the meeting? If you're not listening or anything, just inform the same to him. Okay. Okay, right. Whatever if you have doubts, anything you can ask. I think, is Prachetan present? I think Prachetan is not there. Who is this QCOM BTD? Please write down, replace with your rule numbers or with your names, so that the Hassan can able to give you the attendance, right? If you're not giving, okay, Prachetan is not there. Very good. Laterals are not coming, not listening in the class. Okay, anyway. Okay, Hassan, send me the attendance, okay? Okay, in this session, we have discussed about the common emitter configuration. In the tomorrow session, we'll discuss about this common collector configuration. Okay, then after that one, we'll try to compare the 3 configurations so that BJT, bipolar junction transistor, will get completed, and we'll move to field effect transistor, right? Okay, thank you all of you.